All right, let's get started. Welcome, everybody. My name is Chester Chen, and so in case you didn't find the right place, this is San Francisco Big Analytics. So welcome, everybody. So San Francisco Analytics has been around for several years, and actually this is our first time being in LinkedIn. So we'd like to take this opportunity to thank you very much for LinkedIn to hosting us. So it's a great place, and yeah, give a round of applause. Yes. So they're gonna record the videos, and also on the other, I don't know where the bill is. They also use a Zoom to try to take a webinar and streaming the video out. But in case you didn't see that or you want to take some notes, the LinkedIn will later on give me the video. I'll post it in the YouTube and then post on the Meetup page. So I'm gonna pass the mic to LinkedIn and let me introduce the speakers for the rest of the event.
Thank you, Chester. Please give him a big hand because of him, we have over 600 RSVPs or something. So on behalf of LinkedIn, I want to thank you for giving co-hosting this meetup with us. We have 3 incredible talks today. And the format is really nice. We have food, talks, and food again, right? So there will be hopefully more food at the end. And I was told those cheesecakes are extremely delicious, and they come with 0 calories. So feel free. Right. So first up, we have Jeremy from Google. If you ask people today, you know, which is the hottest open source thing that is going on right now, most people would say it's Kubernetes, and Kubeflow is actually even hotter, right? So we'll see why that's the case. So next up, Jeremy, wherever you are. Okay, there you are, all right. Thank you. Please give him a big hands to Jeremy.
So can everybody hear me? Thank you all for coming, and thank you LinkedIn for hosting, and Chester and for inviting me. I'm going to move for hosting. So I'm Jeremy, I'm an engineer at Google, and I work on Kubeflow, and today I'm going to talk to you about how you go about building ML products with Kubeflow. So basically, okay, hang on. It says it's waiting for the host to start the meetup. So. Screen. Good. Unmute me. All right, we're just trying to get the Zoom conference going. I don't think it would share audio through my computer, would it? Because I don't have my microphone plugged in. Okay, so all right, sorry for that interruption. Hopefully that's all working now. So the agenda basically is I'll provide some background on Kubeflow, you know, what it is, the rationale for it, and then we're going to go through an end-to-end example, walking through how you'd build a relatively simple ML product today with Kubeflow and how that helps you. And then finally, we'll summarize with just a brief summary and some roadmap. So ML is kind of ubiquitous these days. It's all the rage, you know, thanks to a lot of products that have really transformed the way we do things, like self-driving cars, AlphaGo, and Google Translate. And there's also lots of ML products from non-Google companies as well. So there's a perception today that if you're building ML products, that the ML product looks like this, where most of the code and infrastructure for that product is about ML, right? So you think of ML, you think very complicated neural networks, a lot of complicated algorithms, a lot of really complicated math. And then around this, core algorithm, you have a bunch of supporting services. You've got some services to do things like data collection. You've got some configuration management for your infrastructure where you're going to be running the product. You've got some feature extraction tooling. You've got some machine resource management tooling. And of course, you actually have to serve your models and deploy them. And then that brings up a whole set of monitoring challenges. So I think there's a real perception that, from where you spend your time and energy is all about the ML code. And what we've learned at Google is that really the ML becomes a very small piece of this, and that you end up spending most of your time and energy around these other supporting services, right? Because what ends up happening is you end up having a distributed system, and once you have a distributed system that's running in production, that brings with it a whole bunch of DevOps challenges. Trying to talk to me through Zoom. I muted them. Sorry if you're on the Zoom. I don't know how to make that work. So this is what we've learned at Google. Operating large-scale ML systems in production. So we've learned that there's lots of DevOps challenges, and that's what we're trying to solve, right? So what we've learned and seen over the past couple of years is that what's really good at solving these DevOps challenges is containers and Kubernetes. And so with Kubeflow, what we're trying to do is make it possible to build portable ML products using Kubernetes, right? So by portable, we want to build ML products that can run anywhere, whether that's in the cloud or in your on-prem data centers, or running locally on your laptop as part of your dev test cycle. So what is Kubeflow specifically? First and foremost, we are a community, and that community is very broad. So we include data scientists, ML researchers, software engineers, product managers. And the reason that what brings us together as a community is that we're all trying to build a ML platform on top of Kubernetes. And the reason that we're coming together as a community to do this is because I think there's a growing realization that building an ML platform is a really big problem, and it's really quite difficult to tackle alone. And this is sort of a lesson that we've taken from the Kubernetes community. So if you go back 2 to 4 years ago, everybody was building different orchestration platforms for containers. Everybody was trying to sort of build their own orchestration platform by themselves. And really what we've seen is that, Kubernetes got going, and I think in part because they built an active and energetic community, and people realized, found ways to build their own products and companies on top of that. And so what we're trying to do is we're trying to build a Kubernetes native platform for ML. And so what we mean by that is a couple things. First and foremost, we want to run wherever Kubernetes runs. So we're using Kubernetes as our portability layer. So Kubernetes provides a lot of high-level abstractions and patterns for building distributed systems. It also runs pretty much everywhere in terms of on-prem, on your laptop, in the cloud. So if we build a Kubernetes native platform, then we should be very portable and be able to move that platform wherever Kubernetes runs. And as part of that, we're trying to take advantage of Kubernetes patterns and abstractions to manage ML tasks. So as an example, in Kubernetes, there's a concept of a custom resource, which allows you to manage distributed systems, whether that's etcd or rollouts for your servers. And so we've taken advantage of this customizability to build custom resources for managing ML tasks, like distributed training and then model deployment. And then as part of being Kubernetes native, we're seeing a lot of patterns and conventions emerge in the Kubernetes community. As an example, it's all about microservices and managing infrastructure declaratively. So we're trying to take advantage of those patterns and bake them into our platform so that it feels very native and natural to people familiar with Kubernetes. And then finally, specifically, what we provide is we provide ksonnet packages. That's a configuration management tool for managing infrastructure declaratively and deploying all the different microservices and packages you need as part of your ML platform. And one of our goals is to support multiple frameworks. So we want to support not just TensorFlow, but we also are adding support for PyTorch, as well as other frameworks like scikit-learn and XGBoost. And then finally, one of the things that we want to do is we want to provide end-to-end solutions illustrating how ML products get built on Kubeflow. And that's one of the things I'm going to be demonstrating today. So let's walk through an end-to-end example. So typically you would start by deploying Kubeflow, and you can deploy Kubeflow either on-premise or in cloud. And so this is an example. Let me see if I can play this. This is a video that was a tool that was built by Canonical, which is one of our partners. And they've built this little wizard that walks you through basically setting up your Kubeflow deployment, and then it will automatically sort of provision a Kubernetes cluster and then deploy Kubernetes as you need, as needed, and then configure and deploy Kubeflow on top of that. And so these just filling out various options. And then we're building similar tools to run on other platforms like GCP. Okay, so if you're trying to solve an ML problem at a high level, this is a schematic of what it might look like, that workflow might look like. So first you would identify a problem, then you would do a little bit of ad hoc experimentation, exploration to see whether you actually can solve this problem using machine learning. Then you'd probably try to train a model, then you'd try to deploy that model, and then you would have to operate that model and system in production. And this tends to be an iterative process. So after you've deployed the model, you'll go back and do some more experimentations and use those experiments to refine your model. So let's start with an example problem. So one of the example problems that we can think of is if you're managing an open source project, so you have a project in GitHub, you often run into this problem where you have GitHub issues with uninformative titles. So a typical example is a user might file a bug, and they don't know what's going on or what's wrong, so they file a generic title like X doesn't work. So after you go through and debug the issue and help them out, you identify what the problem is. You might want to go back and update the title to make it easier to find this issue in the future and maintain the health and hygiene of your repository. So as a specific example, this is one of the issues that we had in our Kubeflow repository. So a user filed an issue with some setting problems. A new guy needs a little help, which isn't very descriptive. After we went through that and triaged it, we updated the title with a more specific title based on the error message. So this is what you'd really like to do, is keep these titles up to date, but that entails a lot of toil. And so this is an area that would be ripe for automation by using machine learning to see whether you can automatically generate titles based on issues so that you can automatically update them. So let's go through a demo. So if you were starting, typically the first step is you want to do some exploration and experimentation. So typically for that, you would want to use a tool like Jupyter. So that's your very friendly data scientist environment, so that you can do some interactive data analysis to explore data and see whether there's signal there. So as part of Kubeflow, we deploy Jupyter Hub on Kubernetes. So Jupyter Hub is a multi-user notebook server, and this makes it really easy to provision for your different data scientists' notebooks. And you can take advantage of Kubernetes to do resource management. So you can take advantage of auto-scaling to automatically provision more nodes or more resources in your cluster if you have more users. And you can also provision resources like GPUs and more RAM to the notebooks as needed. So in this case, I have a notebook, and this is a notebook that was built by Hemal Hussain at GitHub. So he was the data scientist who came up with this example and published a blog post about it. And so if we go through the notebook, he basically starts out with downloading some data, and then he samples the data a little bit because it's too big to process sort of interactively in his notebook. He does some initial exploration. So here he's just printing out what that data looks like so you can get a sense of what features are in the data. And so in this case, it's just he's reading from a BigQuery table where they have different, each row corresponds to a GitHub issue. So they have columns like issue URL, issue title, etc. He then does some pre-processing. So in this particular case, he's building a text model. So he does some generic, some standard natural language processing, like building a vocab. And that's what he's doing here. Here he's using, I think, using parts of keras to do this standard vocab generation. And also he's tokenizing the text. And then down here, he's actually defining his neural network to generate titles. And you can see down here, he's defining the model architecture. And if we actually print out, we can actually print out a graph here of what the model looks like. And then down here, he trains the model. Nothing particularly spectacular there. And then finally, after he trains the model, he can do some examples, compute some evaluation metrics on the holdout data set. And then in this case, he can actually put some examples into it. So he's put in an example here, which is the body of the issue. And then this is the actual title that gets generated. So this is great. He went through and did an initial experimentation and exploration and proved that he could build a model. But as part of doing that, he only trained on a small set of data. And so to build a higher quality model, he probably would want to scale out and run for a really long time using more resources. In particular, he might want to run distributed training. So for that, with Kubeflow, we provide, as I said, a custom resource for doing distributed training on Kubernetes. And so one of the challenges of doing distributed training with TensorFlow is that you end up having to manage multiple processes. So you have a parameter server, which is basically a distributed key value store for your parameters. You then have the workers that are actually computing the gradient updates. And then you have your master, which is doing all the coordination of these gradient updates and applying them to the parameters. And so you have to manage all these processes. And so you can do it natively yourself, but we've gone ahead and built a custom resource to do this. And so the way that Kubernetes works, I don't know how familiar people are with Kubernetes, but you have a declarative spec. And in that declarative spec, you define what you want to run. So in this case, we have a spec. And then in the template for the spec, we can specify all the different TensorFlow processes. So in this case, we're not running distributed, so we have a single replica. And then down here, we specify the replica type, which is what function this replica is going to be performing in our job. So in this case, this is the master. And then in the pod template spec, we can specify the Docker image that contains our code, and then the actual command that we want to run. And so that's how we can go ahead and launch that, and then that can run asynchronously, unlike our notebook environment, which is sort of an interactive environment. And so we can launch a whole bunch of these jobs and use a lot of resources to train really high-quality models. And then switching back, so if you're training your models with TensorFlow, you probably want to use TensorBoard to visualize your results. Not sure why it's having oh, there it goes. So we make it really easy with Kubeflow to deploy TensorBoard, so you can see the results and quality of your model. And then we wire that TensorBoard up through Ingress and reverse proxy so that you can access it from outside your Kubernetes cluster. Once you have your model trained, then you actually have to go and deploy it. And so that we provide integration with a bunch of different model servers. So you can use TensorFlow serving, or you can use Seldon. And Seldon provides, let me show it. So Seldon provides a custom resource to manage rolling out models, machine learning models into production. So in this case, we've gone ahead and created a Seldon deployment to deploy our model. And so this is what that spec looks like. So just as with our TF job, we have our declarative YAML spec that specifies what we want to roll out. And in this case, we specify a Docker image, which is the Docker image for the model that we built from the trained keras model. And so we can go roll that out into production. And then we also, in this case, might want to have a front-end UI that provides a web app. So this is the web app that we sort of built. So in this case, we entered a GitHub issue. You can then click generate title. It would go and fetch the body of that GitHub issue, then feeds that into the title, into the model, and then it generates the title, which in this case is fairly accurate for what the actual problem was. So switching back. So to summarize, this is what our final system ended up looking like, right? So we started off by doing some experimentation and exploration to see whether we could actually solve this problem. And so for that, we went ahead and deployed Jupyter Hub so that we could give our data scientists a useful environment. Once we were done doing some experimentation and exploration, we had to train at scale. So we had to go and deploy our TensorFlow job controller so we could run TensorFlow jobs. To support our TensorFlow jobs, we had to go and launch TensorBoard so we could see what our models were doing. Once we were done training, we had to go and deploy these models. So for that, we took advantage of the Selden controller. So we had to go and deploy that, and then use that to deploy our actual models, along with our web front end, which is actually providing a web app. Since we have multiple services running in production, we want to take advantage of something like Istio to provide monitoring and telemetry data. And now, since we have multiple microservices that are web services, we need a way to access them. So for that, we're taking advantage of Ambassador, which is a reverse proxy. And then we want to be able to access this from outside the cluster. So we have to connect this to a load balancer. And then since we are accessing it from the outside world, we need to secure it. So we need to connect it with external authentication so we can only let trusted users in. So even though our system and problem is relatively simple compared to some of the other ML examples out there, we still quickly end up in this case where we're running a distributed system with multiple microservices, and we need to keep those up and healthy in order to build successful ML products. So here's our roadmap. So we released our first 0.1 release in April, and that included some core components. So we include Argo, which is a Kubernetes native workflow scheduler. We have Jupyter Hub. We have our initial release of TF Job, which is our TensorFlow job controller. We're integrating with Selden, which provides a CRD for model deployments. And then we also provide support for TensorFlow serving. We're releasing our 0.2 release at the end of this month. So we have some new components coming. So we have Katsib, which is a hyperparameter tuning system. We're adding support for PyTorch. We're adding support for batch inference and Horvath. That's an MPI framework for TensorFlow from Uber. And then we have some other improvements like a click-to-deploy solution. And then we're targeting our 1.0 release, hopefully by the end of the year, at Kubecon in December. So to summarize, if you're building ML products, you end up with distributed systems that bring with them significant DevOps challenges. And with Kubeflow, we're trying to solve those problems by taking advantage of Kubernetes. So that's my spiel. Be happy to answer any questions. I think we have a couple minutes left.
I have a mic here, so if you have questions, feel free to.
Jeremy, thanks for a great talk. And I got a question for you. So how does it compare to the ML Flow, which is just announced at Spark Summit?
I don't really know. I'm not too familiar with ML Flow, so I can't comment. I don't really know what they're doing. So.
Thanks for the talk. So you're in a corporate environment. Let's say if you want to use this, you want to integrate with your corporate authentication. For example, how does this work for Kubeflow?
So we're looking to Kubernetes to provide a lot of those integrations. It's still one of the areas that's underdeveloped in Kubernetes, but eventually we'd like, there's some integration like with Kubernetes with like your existing IAM systems like LDAP and your other OAuth providers. There's some additional work to map that into the permissions inside your Kubernetes cluster, which is called RBAC. So we're trying to get that functionality in Kubernetes because that's really where it belongs. And then with the Kubeflow community, we're trying to take advantage of that to define sort of sensible policies by default. So, you have a data scientist, user role that has permissions that don't allow them to do things like open up the cluster to the external world because they probably shouldn't be allowed to do that.
Another question is, does it come with a storage solution? Let's say for distributed training, most of the time you probably need a distributed file system.
Yeah, so we're trying to find, so Kubernetes is not a storage system, but they provide abstractions in the form of their volume management system that allows you to interact with different types of file systems, right? So you can create a volume for like an NFS share, and then you can attach those volumes to your pods so that you can read and write from them as part of your TensorFlow jobs. And then you can also speak directly to object stores like GCS or S3 or even HDFS. And then the problem becomes, how do you take advantage of Kubernetes patterns to inject appropriate credentials into your pods? And so that's the kinds of problems that we're trying to solve with Kubeflow and make really seamless for data scientists and ML research. Any other questions? All right, if not, thank you very much.
Thank you very much. I was told that in the next meetup, we are going to have a Kubeflow-based ML model to predict how much food to order. So we are right now out of food, but more food is being ordered, and pizza would be here by 7:45 or so. So before I introduce Min, who is our next speaker, I want to just give an idea about what we are doing here at LinkedIn and a little bit of context around our meetup series here. So our meetup series is called Big Data Meetup. Our organization and in general LinkedIn, we are heavy on open source. Just teams around me include several open source products like Azkaban, Pinot, Goblin, Dr. Elephant, Dynamometer, which is a new product we just recently launched to test your Hadoop clusters, performance test your Hadoop clusters. So do check that out. We also have Warehouse, which is a metadata repository. And at LinkedIn, we are trying to make all these products work together. So you have some sort of a data management toolkit that you can just install, and you have essentially every solution all the way from batch infrastructure to streaming infrastructure. All right, so next up, we have Min from LinkedIn. Min is a lead engineer here, and I'm very fortunate to have a chance to work with him. He leads our Spark infrastructure, and he and his team has really spent a lot of efforts to make it really world-class. So Min, can you come up? All right, there you go. All right, please give a big hands to Min.
Thanks everyone for coming to this meetup and sort of share about at LinkedIn what we do on top of Spark. So yes, I did. Okay, so as Amir mentioned, right? So I lead the team of the Spark dev team here at LinkedIn. So basically, we one of our main responsibilities is to basically scale the Spark ecosystem at LinkedIn, basically empowering many use cases that people are coming up with at LinkedIn, right? And this particular effort was a interesting collaboration that was done between the Spark team and our PMK team in terms of to basically see what kind of benefits or interesting things we can come up with by combining people who have experiences of building scalable systems on top of Spark ecosystems versus people who have understandings about the graph algorithms and how that's being applied at LinkedIn. So as a result, we come up with some pretty interesting results. Okay, so you probably have seen this type of LinkedIn in maps before, which basically renders all your LinkedIn connections rendered as this beautiful graph. So now imagine what this graph will look like if it actually represents connections among all LinkedIn members. So actually it's going to be like a massive graph with hundreds of millions of vertices and tens of billions of edges. Right, so hidden inside such a massive graph, are many hidden opportunities, for us to identify meaningful and useful information, so that we can provide, better recommendations and services to our members. Right, so in order to explore, such massive graphs, it raises the requirement, to have scalable and performant distributed graph algorithms implementations. So it turns out that in order to implement a scalable and performant distributed graph algorithm, it's a pretty challenging task. And for most distributed graph algorithms, in order for it to become scalable, needs to be able to reduce the amount of data that is being transferred between vertices, as much as possible, so to speed things up. Right. So if you look at the old generation MapReduce based computation engines, it's going to be very sort of inefficient to try to build a scalable distributed graph algorithm on top of that. And this is mostly due to its very limiting computation models. So that would mean that we'll spend more time on developing the algorithms as well as for running the algorithms. So on the other hand, if you look at those specialized graph engines, so usually in order to, I'm not sharing. Can you confirm it's shared now? Yeah, so we're just talking about, basically, yes. What this means like the vertex of the graph, right? So because most of the distributed graph algorithm implementations on top of a sort of big data computation engines would require sort of transferring or shuffling data between vertices in order to propagate the information to a remote vertex because you're partitioning your graph, right? So that's what I mean by that. All right. So coming back to my the presentations, right? So with the old generation MapReduce based systems, we know it's very limiting because of the computation models, right? But for the specialized graph engines, it also has its own drawbacks because in order to implement distributed graph algorithms on top of that, that usually requires to fit your algorithm onto some generic graph computation models, such as BSP. So while this kind of simplifies the implementation of the algorithm, it also would lead to potential missed opportunities, for further optimization of your the algorithms. So, facing these challenges, we kind of started looking for an alternative. To us, the ideal solution needs to be based on top of a general purpose computation engines, so that have the most flexibilities, to optimize the algorithms. And in addition, of course, it needs to be performant and supporting computation models more complicated than MapReduce. So it turns out that Spark turns out to be the perfect match in this case. In the rest of this talk, I'm actually going to talk about our experiences building a scalable distributed graph algorithms on top of Spark, and throughout the experiences, the various advantages we discovered in Spark that help to ease the implementation as well as improving the performance. So the algorithm that we are looking at, is the random walk algorithm. And random walk algorithm, basically simulates, the behavior of a random walker that moves within a graph by randomly selecting a neighboring vertex to move to until the termination condition is met. right? So this algorithm has many variances, based on differing at how the random walkers determines which vertex in the graph to move to for each step. So this example kind of illustrates one variance of this algorithm. So the random walker will start at a specific source vertex in the graph, and in the beginning of each iteration, it will choose to either move to one of the neighboring vertex, or it could choose to restart the work. So different from other variances of this algorithm, the restart here is personalized, meaning that the random walker will restart from the source vertex or one of its neighboring vertices. So the random walk algorithm has many practical use cases, such as personalized page ranks or representation learning of graph. Right, so the variance that we illustrated earlier can actually be, which we refer to as, personalized random walk. It can actually be used to calculate, personalized page ranks in large-scale graphs. And so personalized page rank, or PPR, it basically identifies, the vertices, that inside a graph, that are important. But from the perspective, of individual vertices, rather than important, globally from the whole graph structure, right? So, this nature of PPR makes it well suited, for generating personalized recommendations of candidate members for our members to connect to, right? So if we have, a sufficient number of random walkers starting from every vertex in the graph, we can be able to gather, enough number of random walk samples. And with those samples, we'll be able to basically get the distribution of the random walkers' positions and using multi-column method. So the result of this can be used to basically calculate the PPR scores for every vertex in the graph. So basically, what the personalized random walk algorithm does, is the following, right? So given a graph G, and this algorithm will basically start n number of random walkers from every single vertex in the graph. It also accepts a restart probability parameter, to basically indicate, the probability that the random walker will restart the work. So notice that, in this case, when the random walker restarts the work, it's kind of equivalent to terminating the current work and start from the source vertex again, due to the restarting probability we mentioned earlier. Right. So another parameter this algorithm accepts is the maximum walk length, so that all the random walkers are terminated after a bounded number of steps. So in here, the parameter number of random walkers as well as the maximum walk length together will actually control the size of random walk samples that we gather towards the end. So taking those inputs, this algorithm will basically produce a collection of vertex pairs, and each one of those pairs will represent a random walk sample, indicating that a random walker starting from vertex S has reached position T. So with the input and output of this algorithm kind of defined, let's take a further look at this algorithm, from the perspective of individual processors, right? So this algorithm itself is multi-stage in nature, right? So in each stage, an individual processor will process all the local random walkers to basically determine their next move. And for each step a random walker takes, there's a probability of alpha that that walker will terminate. Otherwise, the random walker will basically move to one of the neighbors until either the neighboring vertex is on a remote processor or the maximum length, of the work length has been reached. Right. So if the random walker is terminated, it should be kind of gathered as part of the final results. And otherwise, the random worker needs to be sent to the correct remote processor in order to continue the work in the next iteration of the algorithm. So, with this understanding, of the algorithms, we kind of started, looking at, what are the key operations that this algorithm needs to provide. It's basically those three operations that are highlighted here. So, first, the implementation of the algorithm needs to be able to gather the list of the neighbors for a given local vertex. So the algorithm can basically determine, the next moves for all the local random walkers. And second, the implementation also needs to be able to tell, whether a given vertex is local or remote. so that the algorithm can determine when to transition to the next iteration. And last but not least, the algorithm also needs to be able to correctly send the random workers to the remote vertex in order to start the next iteration of the algorithm. So, with this understanding, we kind of start designing, efficient implementations, of those three key operations. So the first thing we looked at is, how can we partition this graph and store, the graph partitions, inside a Spark application, right? So, for the purpose of this personalized random walk algorithm, so representing, the graph partitions as a adjacency list, will be sufficient, for the purpose of the individual processors determining the next move of, each random worker. So, the first thing we actually tried, as implementation on top of Spark is to basically store the graph partitions as an RDD of adjacency list. And, but we quickly realized that, this, implementation is not the most, efficient ones, due to the following reasons. One, even with an adjacency list, it's still not, efficient enough to basically tell whether a given vertex is in local partition or remote. Right, and the other thing is, by representing adjacency list in this RDD format, it doesn't really give us, the most memory efficient usage, right? So facing these kind of challenges, we developed, this custom data structures, to store the graph partitions inside the Spark executor memories. So with this custom data structure, basically each graph partition is represented using 3 integer arrays plus a efficient, integer hash map. So, the integer hash map basically will store the mappings between, the ID of the vertex as well as their local index. So using the local index, that can get us to quickly identify, the corresponding values in the offset and the length integer arrays in order to fetch, the list of destination neighbors or the neighbors, for a given local vertex. Right. So with this, custom data structure, we get 2 kind of benefits. One is it actually supports, both the operation of determining whether a vertex is local or not, as well as, fetching the list of the neighbors for a given vertex, very efficiently. And second, since all those, sort of data are stored in memory compact, format. So, the memory footprint, of this, custom data structure for representing graph partitions are also very efficient. Right. So, while implementing this, kind of custom data structure, we further noticed that, the Spark's multi-core execution model, can, make things even better, right? So we all know that Spark executors supports multi-cores. So usually, people will leverage multi-cores to increase, the parallelisms of their Spark applications. So in our implementation, we kind of noticed that, the multi-core support actually, brings, more benefits. Because, all those multiple cores, actually share the same JVM on the executor, right? So by basically making the graph partition custom data structure mentioned earlier as JVM static and thread safe, it actually allows us to, efficiently share, all those local graph partitions, among all the tasks launched on the same executors. So as a result, the graph itself is actually physically partitioned into only as many parts as the number of executors, this Spark application has. So, with this understandings, basically if we request, for executors, we request for fewer number of Spark executors, but each with, higher number of cores, this will effectively, reduce the total number of graph partitions we have, for partitioning this graph, while still having, sufficient and large number of parallelisms to partition and process, this, graph and execute the algorithms. So by having a smaller number of graph partitions, helps the random walkers to stay within a local partition. This is especially true, if better graph partition techniques are used. Right. So, with this efficient sort of in-memory representation of the graph partitions designed and implemented, the next thing we looked at is remember, the 3 key operations mentioned earlier in the pseudocode, right? So we need to be able to fetch the list of neighbors. We need to be able to tell, which is remote, which is local, right? Those 2 are supported by the custom data structure. But the next thing is, how do you send, the random workers to the correct remote vertex, when, the workers works to a, remote partition, right? So this is the next thing that we looked at, in our algorithm design implementation. So we noticed that this algorithm itself is kind of iterative and can be divided into multiple stages, right? So as illustrating this diagram, in each stage of this algorithm, a portion of the random walkers will be terminated due to the restart probability, and the remaining continued random walkers will continue on to the next stage in order to continue the next iteration of the algorithm. And that requires, all those continued walkers to be correctly sent to the remote vertices where the corresponding graph partitions is stored, right? So when all the random walkers are finished, all of them are aggregated together to form the final results, representing, the random walk samples we gathered towards the end, right? So, to illustrate, using a simple graph and a single random walker, right? So, in this graph, we have, basically 4 vertices, and they are divided into 2 partitions stored onto 2 executors, right? And a single random walker starting from vertex 1 decides to first move to vertex 3, then vertex 4, right? So all those intermediate steps that, this random walker works to is recorded as this tuple of source and current position, representing, the starting position of this random walker as well as, its current position. So when this random walker gets to vertex 4, because vertex 4 is actually stored on executor 2, so it actually needs to be sent to executor 2 in order to continue the random walk, right? So this will basically terminate, the first stage of this algorithm, and further requires, routing the random walkers to executor 2 based on its current position in order to continue the algorithm. So in the next iteration of this algorithm, the random walkers are sent to executor 2 and based on some kind of routing informations. And once it's there, it will be able to continue the work and eventually terminates, right? So, looking at, this simple example, one straightforward way to, implement this routing mechanism is by basically performing a join between the random walker datasets and the graph partition datasets. Based on the the current positions of the random walkers at the end of each stage, as well as the vertex IDs stored in the graph partitions, right? So this will guarantee that it always lead to the random walkers to be co-located with the correct graph partitions after the join. However, this approach has 2 main issues. One is it actually requires, shuffling both the random walker datasets as well as the graph partition dataset. So that will lead to, too much data transferring between stages. And the other problem is, if we want to be able to join, the graph partitions with random walker datasets, that also means we're not able to store the graph partition datasets, using the custom efficient data structures that we mentioned earlier. So, with these, issues, we kind of, looked at, what Spark can actually provide to help with, this situation. And we realized that, the Spark's zip partition operator actually is the perfect solution here. So what Spark's zip partition operator does is it's basically going to, co-locate, the 2 co-partition RDD partitions together, right? And then in addition, if one of the RDDs is already pre-partitioned and persisted on the executors, so the zip partition operators will effectively deliver, the shuffled partitions of the other RDDs onto the executors, storing the corresponding, partitions from the persistent RDDs, right? So, with this observation of the Spark zip partition operators behavior, so we implemented, this following routing mechanism, illustrated using the same simple example here. Right. So basically, what we're doing is, when we are storing or storing the graph partitions on the executors, we also start generating a routing RDDs. So those routing RDDs are basically generated from the graph partition themselves, where each element is keyed by the the partition IDs of the corresponding graph partition, and stores some metadata representing that graph partition itself. So basically, this routing RDD is only going to have as many elements as the number of partitions that we partition the graph data into, right? So once we have this routing RDDs generated, we further persist, this routing RDDs onto the Spark executors. So after persisting this, what we ended up having is the routing RDDs themselves will start recording, which graph partitions are stored on which Spark executors. So now with this routing RDDs, it can really serve, the purpose of a routing table to deliver the random worker datasets, to the correct executors storing the graph partitions. So what we are essentially doing is, like I mentioned earlier, right? Zip partitions requires two RDDs to be co-partitioned. So as far as we're partitioning the random worker datasets based on its current positions at the end of the stage using the partitioner of the routing RDDs. And the zip partition itself will guarantee that where it is effectively delivering the random worker partitions to the correct executors where the correct graph partitions are stored. So after this, we are able to, co-partition, the random worker datasets as well as, the graph partitions stored in Spark executors in that customized data structure, right? So with this approach, and we're basically getting, a couple benefits, right? So one is, like I mentioned earlier, the size of the routing RDD itself is extremely small because it only has as many elements as the number of graph partitions. And also, it's only storing metadata. And the other thing is, since now the join operation is done between the random worker datasets and the routing RDDs, the graph partition itself is decoupled from this join operation. So that enables us to continue storing the graph partition using this memory efficient data structure. And as a result, that also means, we don't really have to shuffle the graph partition datasets. And at the end of each stage, only the random worker datasets needs to be shuffled, right? So with these benefits, we essentially get, a very efficient mechanism for delivering the random workers to the correct remote vertex. So the next thing we looked at is, how can we further optimize the algorithm itself? Because the algorithm at its current stage is still not scalable enough. And this is mostly because, all the random workers are started at once. So this will cause too much data to be shuffled, and especially in the initial stages. So we observed that, actually instead of starting all the random workers in the beginning, we can actually start the random workers in an incremental fashion. So this way, in each stage, there will be some random workers starting and some random workers terminating due to the restart probability. So, then eventually once the new workers and the terminated workers in a stage balance off, that will also means, the total number of random worker, that we need to process in a stage is also bounded. So, by basically controlling the percentage of the random workers to start in each stage, we are effectively able to bound, the maximum number of random workers we need to process in each stage. And actually, this should be controlled by, the result of this formula, where the P represents the percentage random workers starting per stage, right? So, this mechanism basically gives us, the ability to trade off between the max number of random workers to process in each stage versus the total number of stages. So as a result, if your graph data is small, you probably want to do it faster, and you are able to, basically start, more samples more quickly, because you want to reduce number of stages, and you think the the workload to be shuffled is handleable. However, if you are starting dealing with a large-scale, very massive graph, it also gives you the ability of to sort of put a threshold in terms of the max number of data to be shuffled between stages. But as a result, it will generate more stages. So this is further illustrated in this diagram, right? So in this example, we are starting 10% of the random walk samples in the initial stages. So this way we're kind of spreading out the entire overhead of generating and shuffling those random walkers across the initial 10 stages. So although this will lead to more stages, compared to if you just generate all those random walkers in the very first stage, but more importantly, it gives us the ability to bound the maximum number of random walkers to process in each stage, and the maximum amount of data to be shuffled per stage. So we further noticed that the Spark's shuffle file management mechanism further makes this incremental processing of random walkers, even more efficient. So at the end of each stage, the random walkers being shuffled will include both the terminated as well as, the continued workers. So this will generate, a set of shuffle files for each stage. Spark's shuffle file management mechanism will enable us to effectively reuse, those shuffle files twice. Once between the stages, when delivering the continued workers to the next stage, and once towards the end, when Spark is gathering all the terminated workers to form the final results. So, this will enable us, to basically effectively process, all those random workers incrementally and aggregate the results, towards the end, using a single shuffle, right? So basically, at this time, we kind of implemented, those 3 key operations, mentioned at the beginning of the pseudocode, right? So the ability to, determining the list of neighbors and determining whether a vertex is local or remote, as well as, sending the vertex to the correct remote, sending the workers to the correct remote vertex. And in addition, we also leverage, Spark's shuffle file mechanism to further optimize this algorithm, implementation by leveraging, an incremental fashion of, starting these algorithms. So, to further evaluate this algorithm, we actually perform the benchmark, basically say, with all those controlling parameters we have, what are our abilities to kind of, moving things around a bit. So, in terms of the setup, this benchmark, we used a small fraction of the, actuators or resources we have on our shared, Yarn Hadoop clusters. And, sort of those actuators basically have 10 G memory and 10 vCores. And we took the entire LinkedIn member connection graph, as the input for, implementing or playing with, this implementing algorithms. And in terms of the parameters, we choose 500 sort of random walkers, and with, the restart probability being 0.4, and the maximum work length to be 20. Right. So the first thing we looked at is, whether, the efficient, sort of in-memory data structure implementation of the graph partitions actually gives us, significant storage gains. And we compare, if we just store the graph, as the RDD of JSON's list versus storing the graph using the custom data structure introduced earlier, right? So we actually noticed, more than, 10% of the, the storage savings when storing, those graphs in memory. So the next thing we looked at is, remember there's this, parameters to basically control the incremental start of the workers, right? And to basically be able to bound, the maximum number of shuffle, across the stages. So, the next benchmark we did is to basically say that by increasing the percentage of the workers we start per stage, how that impacts, the maximum shuffles per stage, as well as, the maximum stage runtime. So we actually noticed a kind of a very clear sort of linear growth, between the percent of workers we're starting versus, the amount of workload that each stage needs to process. So, keep in mind that those numbers basically represents, the maximum data needs to be processed, as well as, the maximum stage runtime. Because, once the, all the random workers are generated, so each following stage will process, a smaller and smaller amount of data, because, each stage, will have, a certain percentage of the workers terminated. And the next benchmark we're comparing is basically the trade-off between the workload per stage versus the total number of stages, right? So one thing mentioned earlier is, you can actually are able to, either, have more number of, stages created in the, in the algorithm in order to spread the load across more stages, or you can, do it within a smaller number of stages. So this benchmark we're doing here, basically, demonstrates that, for a particular workload of the graph that you're dealing with, and there's actually a sweet spot, where you can sort of, identify, the right number of percentage of, the samples to start in each individual stage. That will get you, the best total number of runtime, for the entire algorithm. So to conclude, right? So from this experiences of, designing and implementing this scalable and performant sort of distributed random walk algorithm on top of Spark, we learned quite a few things with Spark itself as well. So first, Spark's programming interface, enables sort of a very performant and very powerful operations, so without having, to program too much. The second, Spark's, sophisticated sort of shuffle management, as well as, its, very good performance, combined with a good algorithm, design and optimization, will lead to a very efficient, scalable graph algorithm implementations. So, that's the end of this talk. And any questions? You mean in the benchmark itself? Okay, yes. So
can you repeat the question?
Yes, will do. So the question was, how the graph was, partitioned, right? So, so the thing is, like mentioned earlier, right? So basically, you want to request, actuators with higher number of vCores, so that the physical number of partitions, this graph is partitioning to is basically the number of actuators you have. So that means, the physical partitions this graph has is, 200, right? However, you're able to have a much larger number of parallelisms and, the actual graph partitions, right? So in this case, with 200 actuators and 10 vCores per actuator, your sort of processing parallelism is actually 2,000. But, you can further partition your graph onto, 20,000. If you feel that, each individual task, the amount of data that each individual task needs to be kind of bounded towards a certain size. So I think, in this benchmark itself, we're actually, setting the total number of Spark partitions to be, 20,000, where the total number of parallelism is 2,000 in this case. And, the actual physical partitions of the graph is only 200, because, all the local graph partitions are shared between all the tasks launched in the same executor. Yeah. So are you referring to
can you repeat the question? Yeah, if you have questions, it would be great if you guys can come here and ask the question from you.
Yeah, so are you referring to if the activated nodes will not be visited again? Okay, so, in this case, because, what we really want to do is to, okay, I'll repeat the question. So the question was, if we're maintaining any activity state, for those, visited vertices, and making sure that we're not visiting those vertices again, right? So, the purpose of this algorithm itself is to basically identify, the sort of important sort of vertices, from the perspective of each individual vertices, right? So what that means is you actually do not want to skip, an already visited vertex, because, by basically counting, the number of times the vertex is actually visited, starting from a given source vertex. That's how you are able to basically determine the probability that, a certain vertex, within a given source vertex local network, how likelihood, it is for that vertex to be reached. And, the vertex that has a higher probability, will basically be treated as, the important vertex within the source vertex, sort of the local network, right? So in that case, you don't really want to skip an already visited vertex. And in fact, that's what you want to do, so that, towards the end, you can use Monte Carlo method to kind of, estimate, the sort of distribution of the random walkers positions. Yeah. Yes. Sorry, I can't hear. You mean the alpha value? Okay, the question is, how do we determine the alpha value? So I think, that's basically, I don't think there's actually a good sort of mechanism to determining the alpha value here. I think this is probably more like, a heuristic, other than, there's actually, sort of some experimentations with different alpha values and choosing the ones, that's used best. Yeah. Yeah.
So in the market, there are a lot of tools are available, like Tableau and other tools. How do you compare with the Spark, especially for the graphical thing, with other tools like Tableau and other tools?
Tableau?
For the graphical thing for the reporting purpose or something. At the end output is going to be used for some reporting, right? So there is a lot of reporting tool for the big data. So how this Spark Capital is going to differ from the other tools, other BA tools?
So I think the question is a little bit unrelated to this presentation, but I can also give you my perspectives for that particular thing. So I think Spark itself is not really a reporting tool, right? It's rather a sort of a computation engine for actually generating those reports. Yeah. Right. Yeah. Okay. Yeah. So when we talk about graph here, what we're really talking about is like, how do we use Spark to analyze a graph, right? So not really generating a graph, such as, those BA tools that you're using for visualizing, the results. I think that's the difference.
Thank you for a nice presentation. My question is on the value of alpha. Is there any intuition on setting alpha to 0.4?
Like I mentioned earlier, right? So,
yeah. The related question would be that in some cases you may run into like a focus stack into one of the executor, like stack into one of the part of the graph and then walk randomly there instead of jumping to any other executor that can run. Will this cause performance issue or not really at all?
Are you referring to like, if there's like, a vertex in the graph that has, many, incoming edges, that will cause, so basically, with, this algorithm, that's essentially what you really want to discover, right? So that's like, how you basically discover that, within a vertex local networks, which is the vertex that are more likely to be visited, right? So, essentially this algorithm it wants to do that. But in terms of the performance of the algorithms, that actually won't really have any impact in terms of, generating skills. Because what you are shuffling is, so that's what makes, this algorithm kind of a, the skill of the graph itself, like in terms of how many, incoming edges to a particular vertex, won't really impact, the distribution of the random walkers that you're shuffling, between those executors.
I have a question. I assume the previous implementation was in MapReduce. I was wondering if you could tell us what was the resource usage previously, and then what sort of performance improvement you obtained by switching to this Spark.
Yeah, I don't think I still have the numbers of the old states. Although I think at some time I did have access to that, because the old implementation is also doing things slightly differently in the sense of the MapReduce itself is not really scalable enough. So what actually ended up happening is basically each I think it's each or maybe a couple of days per week, the MapReduce based implementation will actually just take one step, for the random walker. Instead of, in this particular implementation, what we're doing is we're able to do, n number of steps within one execution of the algorithm. So I think, that was basically one main difference. So if you kind of compare it, more like, the MapReduce based implementations will, pace, this random walks across multiple days, where, each day it would just move one step forward. Right, so then the execution overhead of that particular job itself is kind of small, but you're sort of in order to reach a large enough or representative enough samples of the representation of the graph for each vertex local networks, that requires also multiple days in order to have the workers work enough number of steps before you gather the samples.
Right. Any more questions? No? All right.
Thank you.
All right. Thank you, Min. All right. I have a question before I start the next one. How many of you have actually done your own DNA test or something like that? There's one, right? Okay, there are a few. Oh yeah, awesome. Actually, if you have seen your own, I did it last month actually, and if you see the results, they're actually quite incredible. You know, the amount of data it has is very fascinating. So the next talk is related to that. So that's why I wanted to bring that up. I was reading it somewhere and they said in the last 50 years, you know, 3 very small things have changed the world by a lot. You know, one is atom for the nuclear side, right? And then we have bits on the computer revolution, and the last is a gene, right, which is changing a lot of things around it. So the next talk we have from Bradley from Google. He's going to talk to us about the confluence of data, machine learning, and genomics, which is quite a fascinating topic to look into. All right, are you all set? All right, awesome. And there's some more pizza. But all right, thanks. Please give a big round of applause to Bradley.
Thank you. Oh. I think I did. Oh, no, not. All right, my name is Bradley, and I work in Google Cloud. And today I'm going to talk about a genomics project that I have been working on by partnering with some researchers from Princeton University. So I'm going to share my experience in doing genomics researches in Google Cloud, and also show a little bit how do we convert like research problems and finally turn it into engineering problems, and also share some of my views towards genomics as an outsider of that kind of science. So I will start by setting a few contexts. So let's first take a look at the intelligence evolution. So there are a couple of stages. There are actually more sub-stages, but I'll just group them into 3. So first, nature has been driving the intelligence evolution for billions of years by randomly mutating some of our DNA's very small portion, generation by generation. Sorry, let me double check. Okay, I'm not sure how. Oh, is it because I didn't join the meeting? Oh, I see. All right. So nature has been driving the evolution by changing our DNA little by little, generation by generation, and the scale is very small. So for example, for human beings, by average, only less than 100 DNA base pair is being changed by 1 generation. And compared to you have 3 billion base pairs. So it's a very, very slow process. And also it's a very inefficient system. If I were to design this system, I won't do it this way because it's basically a try and error. And the problem is there's no database to keep track of what are the failures, what are the success of certain mutations. If it makes some mistakes, made a bad mutation causes it to be unsuccessful, that kind of mutation will happen again. So that's why it's a very slow and inefficient process. And in the second stage, there were very smart animals that they can simulate some of the try and error in their mind. They can do what if in their mind. And then later, it also comes with human being, with language, with math, and also with artificial intelligence. So we have been changing nature at various levels with exceedingly faster and faster pace. We change the nature, we change our environment from like molecule level to atom level to subatom level. But the nature has been changing us in an unchanged pace for billions of years. And it is doing it today. Sorry, I don't know how to quit this guy. Okay, there you go. Okay, so how many of you heard about singularity? Almost everyone, right? Yeah, so it's a very hot topic. And basically singularity means at some point there will be a super intelligence that is so smart so that it can improve itself recursively. So in a very short period of time, it will achieve tremendous explosive improvements and lead the world to an unknown state. So we think there are two paths to singularity. And the first path is we human being as a carbon-based intelligent being, we design better and better silicon-based, chip-based machines. And to the point that at some time, the machine will be smart enough, will outsmart human and start improving itself. And if you look at the other path, we as a human, we design better and better machines, and then we can use these machines to improve ourselves. So it's a closed loop. And what genomics is so critical is because it basically closes the loop by providing the link from silicon to carbon, the red link as shown in my slide. And yet, a lot of years later, so the outcome, it could be a superhuman, or it could be a super machine, or it could be a hybrid. We don't know. I would argue the second path is more efficient because you don't start from scratch, and your human brain is your starting point. So also talk a little bit on the DNA sequence. So every intelligent being, the physical state of that intelligent being are determined by how many proteins of each kind and what time in what organ. Like for example, your health is very much related to like every midnight how many certain proteins are produced in your liver cell. So what, when, and where are critical. And in DNAs, there are coding regions, and we call them genes. Basically, these are the templates of proteins. And each protein is basically a sequence of amino acids. And these, each protein, the combination of the sequence is always the same for the same type of protein. And how does it keep track of like reproducing the protein with the same sequence? So the fact is there are certain regions in our DNA that are basically the templates of these proteins. And it constitutes about 1% of our DNA sequence. And they basically determine what kind of proteins it will produce. And there are non-coding regions that controls the gene expression. So this is what they call epigenomics, not genomics. So basically, instead of researching on the genes that are templates of proteins, they research on the regulation activities on these genes. So these regulators, they determine how much and when and where these proteins will be produced. And also, in the meantime, there are still over 90% of the DNA sequence. We still don't know what their functions are. So if you look at the DNA, it's like an operating system. It's a software stack. And we are slowly reverse engineering that operating system. And the purpose of that operating system is basically to produce the right amount of proteins of each kind at the right time in the right environment. And Deepsea is a project initiated by Jianzhou and Olga. It predicts these non-coding functions or we call the regulator activities, given the DNA sequence only. I'll expand into more details later. So the motivation of the Deepsea is, so first of all, predictions based on the DNA sequence, based on raw DNA sequence to predict the phenotypes are really hard. Why? Because first of all, there are only limited people in the world, and compared to the infinite DNA mutations, DNA sequences. And second, you have a lot of privacy concerns. These medical data are really hard to gather. And also the data is pretty expensive to collect. And the data sometimes are sometimes are very low quality and very subjective. For example, so I participated in autism research by predicting autism spectrum using DNA sequence. And we only had about a few hundred positive autism instances. And the way they collect, they decide the autism spectrum is basically asking you 20 questions, and based on the answer, they give you an autism score. So this is very subjective. And also training from scratch, from the model to predict the phenotypes based on the DNA sequence, raw DNA sequence is very costly simply because the DNA is so long. There are 3 billion base pairs in each human being. So what Deepsea does is, instead of predicting the phenotypes, which are observable traits, it predicts low-level regulator features. And to be more specific, it predicts 3 types of regulator features: TF binding site, histomarks, and DHS. So I'm not going to expand in more details of these, but think of the whole DNA sequence as an operating system. So these are more like a memory management or threading management, disk management. So each of these have certain functions that controls the gene expression. And what's good about predicting this is the features are labeled automatically in lab. So instead of sending out papers and collecting the phenotypes manually, these features are can be automatically collected and labeled. So all of a sudden you have lots of labeled data. And Deepsea is a shared model that predicting multiple types of non-coding features, the 3 I mentioned earlier. It's a shared model predicting 3. So the benefit is, the 3 labels can influence each other by using a shared model, using shared weights. So given such model, we can generate very informative features from DNA sequence. And then we can use these smaller size features to predict next level, higher level features, including the phenotypes. So this idea is kind of interesting because now it kind of looks like an image model. And in image model, we know that there are transfer learning possibilities, right? The model you build for trained with the millions of images can be used and to predict fewer instances of data. And also with such model, it also helps researchers to understand how these non-coding regions work. It helps the researchers to reverse engineer the DNA sequence, to reverse engineer the operating system that nature gives us. So the features of the data, the dimension is basically 1,000 length DNA sequence, and each unit is basically it's one of ATCG letters. And it predicts around 900 binary outputs. Basically, given a DNA sequence with 1,000 length, it predicts whether it's a TF binding site, whether it's a DHS site, or whether it's a histomarks. And the size is about 3.3 gigabytes, and instance is about 344 million. So we started with this set, and it's already very big. And if you look at the model, so the model is TensorFlow based. I tried different hyperparameters, and what I found is the deeper the model gets, the better the results I can get. So I ended up with this 10 layers of convolutional models, and if you look at this, it's very much like an image model, like Inception. And this is performance. It's about, with 1 million steps, we reached the 93 plus AUC, which is a very, very good number compared to past researchers. Okay, so we started by a CPU single node only with TensorFlow, and it takes forever. It's we roughly estimated that it will take about a year to go through even one epoch. Then we tried the GPU single node. It went down to a few days, and then we tried the distributed training with GPU, and it turned out it didn't work. Why? Because the computation with GPUs are so fast, and the way distributed training works is you have separate parameter servers, you have workers, and these workers keep sending updates to the parameter servers. And because the model is too large and the computation is too fast, it has too much information to send to the parameter servers. And the network in the cloud basically cannot catch up with the speed. So then we switch to multiple GPUs, single node. We do it with 4 P100, with 8 V100, and it goes down to a day. And we're still experimenting cloud TPUs, but we're very optimistic that someday we can get it down to even a few hours. So what Google Cloud offers, so first I think it's the best place for run TensorFlow. There are lots of optimizations specific for TensorFlow. And what is meaningful to the researchers is it provides a serverless training and batch predictions. So that means the researchers, they started by asking, okay, can I get some VMs with P100? And we gave them. And they started logging and installing dependencies and run jobs manually. And soon they found that it doesn't work because there are so many things to manage. So Google Cloud offers a machine learning training and batch prediction services that you don't have to manage all these infrastructure, VMs, you just submit your jobs. And it also gives you a centralized logging, and there's a centralized API. And your GPU and TPU, your resource requirement are basically specified as a job spec. And also, the way TensorFlow works is if you use TF estimator, basically your code for parameter servers or workers or masters are exactly the same. You just write one version of the code, and it will automatically decide, okay, I'm a master, I will run this code path. If I'm a worker, I run this code path. So these researchers, they don't have many TensorFlow engineering background, but very soon they can quickly start by using the TensorFlow estimator-based approach to do their research work. And some of the learnings, so first, deep learning is required on DNA. As you can see, the model depth is very, very deep, right? So it's just like image models. And there are possibilities of transfer learning just like images. And also the managed service for training and prediction is very important because the genomics research, they run lots of data and lots of jobs, and it quickly goes out of control of what they can manage. And we get with the technology improvement on data collection, we get more and more data. The initial 3 gigabytes now it turns into 1 terabyte, and about 900 outputs now becomes more than 20,000 outputs. So we really need faster and faster computation resources. Okay, so why do we do genomics? I think if I have a choice, what I think makes sense is, so all the Google Cloud, AWS, Azure, all these computation resources, if I have a choice, I would all have it doing genomics research because this is a very, very impactful thing to do compared to other things like self-driving car. Because for the first time, we are very, very close to reverse engineering the DNA, that operating system. And soon, I think next step, we can simulate the DNA mutations in computer. And then we have more steps that you can imagine. As of last year, I heard that for the first time, we successfully did our targeted DNA mutation in an embryo cell, which is very exciting and concerning. So, but I think the technology will not, improvements will not stop. It won't stop regardless. So there are lots of opportunities, lots of challenges for genomics. And I personally, I'm very passionate about genomics, about the impact, and I think it deserves more and more attention, and it deserves more and more resource for these researchers to do further very important findings for us. So that's all I have. Thank you. Any questions? Yeah.
So going off the direction.
I think I've never thought about it, but I think it's possible. I think it's totally possible. I think it's a great idea. But I think the building block is to first using the DNA sequence.
Bradley, can you repeat the question, please?
So I think the question is, can we use the Deepsea model as a start to predict the gene history and how does it evolve? I think yes, but I think still by predicting the phenotypes, by reverse engineer the operating system of DNA is the first step, is a building block. Yeah. So I think it's not that hard. I think that the difficult part, the most difficult part for DNA research is actually for many years is data collection. So if I remember correctly, to our 4 DNA sequence is more than a few $1,000s a few years ago. Right now, I think it's cheaper and cheaper, a few $100s. So right now, the problem now is we have more data we can handle. We need to have better software. We need to have better hardware. But the DNA itself is not that complicated. It's just like image. You have low-level features, like you have edges, you have shapes, and then it constitutes low-level features. Then you have higher-level features on top of it. And DNA is the same.
So it's a very interesting talk. So I just had a similar question. So seems like your current focus is trying to investigate on the evolution side and trying to see how we can generate mutation, like which are more beneficial and probably more efficient. But have you considered the fact that human genome is much complex and actually some virus genome is really simple? So would it be possible actually like the machine, trying to push it too hard into like making mutations can actually somehow generating like virus genomes that are potentially like so I mean the speed that we create mutation is going beyond our ability to actually handle these viruses and or detrimental things rather than a good thing. So wouldn't that be more necessary to actually investigate the function of the genes rather than, because we know so little about the genomes right now.
So I'm not a genomics researcher, so I'm not sure I can answer the question correctly, but I think they did do a lot of research based on virus, based on plants, based on like animals, not just human beings. I think not just the human's DNA, there are a lot of other living things' DNA are being investigated and reverse engineered.
And you also mentioned like the size of the data a lot of times. So what are the current solutions for like Google Cloud in terms of data storage?
So data storage, Google Cloud, there's we call it GCS, Google Cloud Storage. And so the size of the data, the storage is not a concern, but the concern is still computation, right? So with only 1 gigs of data, it usually requires lots of computation resource to run several epochs, especially if you have a really deep network. There are lots of computation to be done.
Thank you. Thanks for this very interesting presentation. I also have a question regarding so I think one thing in the big data world that we have starting to see is as technologies evolves and security and privacy is becoming more and more a concern. Right, that applies to both the raw data as well as there's also recent talks about the model privacies, right? We don't want the trained models to be able to extract sort of user privacy information, right? So I'm wondering in the world of DNA and genomes and all of that, do you think a similar problem also applies there? And if so, what are the current thinkings and this particular areas of industry thinking about?
So I'll give you one example. The autism database. I think I applied for the permissions and it got 1 year for me to finally get access to that. So privacy is a big concern. So that's why we started a lot of experiments, not on human beings, but on animals, virus, and whatever. And I'm not sure that at some day we may have built a model with lots of human data. I don't know these aggregated the model is basically an aggregated result of all these data being collected. I'm not sure what kind of privacy implications are on top of that model. So it depends on what kind of data you gather. If it's in the Deepsea model, there are recent technology improvements that enables data collection, they can automatically identify TF binding site, DHS, these kind of things. So these low-level features, they can do it from lab. And for higher-level features like the eye color or the height or weight, these are really hard to collect. You're talking about predicting? Yeah. So as far as Deepsea is concerned, it does not predict very high-level features. It predicts the very low-level features. For example, given a sequence, we know if it is sequenced correctly, it will be a successful TF binding site. If there's a random mutation there, it may cause the TF binding site to not functioning at all. So, and then because the TF binding site is not successful, it will lead to certain proteins not being able to be produced, or you will produce too many of these. So it's a step-by-step, it's a from low level to higher level process.
Thanks for your talk. So you had a slide which had the running times on different architectures, right, or CPUs. So could you briefly comment on accuracy versus computational time that deep learning methods brought to this versus existing state of the art?
So I think the actual model quality is not affected by what kind of hardware it is being run on. It's just a matter of speed.
So I meant compared to non-deep learning methods.
Oh, non-deep learning methods. Sorry. So, okay, so I'll give you one example. Non-deep learning methods in genomics only works in one scenario, that is predicting your ancestry. And for any other phenotypes, it doesn't work so far from what I can see. It requires deep learning.
So in your trained model, I'm really curious about the low-level features. So for images, you can occasionally find things that look like Gabor filters or SIFT features, this sort of things. Did known motifs pop out from those low-level features? Have you shown biologists? Are there interesting things in those low-level features?
I'm sorry, can you repeat the question again?
Sorry. So at the lowest level, so there's lowest levels of your model, the trained features you got out of your model, did they
you show them to a biologist? Did they look interesting? Did they look like known binding motifs?
Yeah.
Did you look at them?
Yeah, so are you asking the low-level features, are these low-level features interesting to the genomics researchers?
Yeah.
Yes, so the three examples that Deepsea predicting, DHS, TF binding site, and histomarks, these are already established concepts in genomics. It's not something new that is being learned from the model. It's just with the help of machine learning, they can identify more and more patterns that they can categorize them into these three categories.
So just to verify, did the model generate those de novo without being, did it find those features on its own?
Yeah, the model finds the features of its own. So for example, the TF binding site, usually before machine learning, the way it works is there's a database tracking all these kind of sequence. Okay, if you hit this sequence, this is a TF binding site. But it doesn't work quickly because there are too many combinations. It has unlimited combinations. So they have to use machine learning to identify all these patterns.
So I think a natural follow-up to that question is you were talking about transfer models. And in the context of these lower-level features becoming more and more meaningful, did you try, for instance, training on 850 or 819 of those outputs and then doing a transfer approach for the remaining 100? And do you see kind of a large improvement that would be supportive then of saying that it found things that really are transferable to other models in other contexts?
So we think that the predicting the low-level feature is the first step. So first of all, it's an interesting question. It's an interesting idea, and we have never tried that. Maybe I should feed back to the researchers and let's gather their thoughts. But I think the current Deepsea is just predicting the low-level features. By transfer learning, I'm more talking about like predicting from DNA to the high-level features, and the model can be reused to predicting others by like just gathering a few layers, bottom layers, and then adding a few more layers on top of that to do another prediction.
One more quick follow-up question. Did you look at the consistency of those embeddings in those like early level low features, just to get a feeling for kind of if you saw two distinct inputs, did they continue to be embedded in the same output space, or was that less consistent or more so?
I see. No, we didn't, and I think it's a very interesting thing to do.
All right, the last question. I'm sure Bradley would be around for at least a few minutes after this, and you guys can go and grab him. Last question. Okay, we have last two questions from the same.
Yes, thanks for the great talk. I noticed that your data set is very large, right? Do you run into the problem of data cleaning before you run the TensorFlow operation?
No, we don't. It's a raw DNA data. We don't know how to clean it.
Okay. So there's no missing data and stuff data?
No.
Okay. That's kind of
surprising. Yeah, that's easier. Yeah, you're right.
Yes. Another question would be on in parallel with this work, there's a kind of work that I try to identify what type of patterns or combination of patterns gives phenotypes or genotypes. And those work are based on the analysis of gradient of backpropagation stuff. I wonder that the infrastructure that provided in the Google Cloud can, in parallel or distributed Google Cloud, can support this kind of analysis or not?
So you're more talking about like linear regression, like
No, not linear regressions. There's a couple of works come out of Stanford regarding the analysis of backpropagation and identify which combination of patterns mean something to particular output. Yeah, I wonder that will those be supported in the distributed environment, or at least not yet?
Okay, I'm not sure about, I don't know the details of that research, but I think it's a regular machine learning, normal machine learning process. So there's a backpropagation process, regardless whether it's distributed or single node. But I'm not sure if the backpropagation in the machine learning here is the same as what you just described.
It's based on CoreOS, so probably the same.
I see, yeah, so it's a machine learning, yeah, so it's probably the same thing.
All right, thank you everyone.